In this video, I'd like to talk about increasing, decreasing functions and how we can use derivatives to determine behavior of the function. So the first thing I want to note is to make sure that when you write increasing, decreasing, or constant behaviors, you're going to write those as open x intervals. So we're specifically looking at the x values. So in this particular problem, I'm given a graph and asked to determine the intervals over which it has the following behaviors. And first, I'll look at increasing. In just a general way, increasing means that my graph is going uphill. So as I look at my graph from left to right, then I'm rising. So we can notice here that my graph would be rising all the way up into that point, and then at that point I start falling. Here I would end up being, looks like constant, and then it looks like here I'd be falling, and then somewhere down in here I start rising again. And so on here, I want to determine the x intervals for which I have this increasing behavior. So what I'll do is I'll start to the far left, it looks like I'm increasing there, and I'll go up to determine the x value where the function starts to increase. Now, we do open intervals only because we don't actually increase or decrease at a single point. So starting at -2, I start my increasing behavior. So I'll do an open parentheses, denoting that I'm not including the -2. And then now I'm going to figure out where my function stops increasing. So it looks like it stops increasing up here at this point. So what's the x value that goes with that? The x value that goes with that is 0. So I say I'm increasing from -2 to 0, not including either one. And then because we have one more interval where it's increasing, we're going to do a union. And then go to the other piece. It looks like I'm increasing from here to here. And so I'm going to go up and I'm going to say determine the x value where I start. Looks like 6. So I'm going to open this up with an open parentheses and say from 6. And then it looks like I'm quit increasing there. So it looks like I go from 6 to 7. So the interval over which I'm increasing is from -2 to 0, union 6 to 7, not including any of the endpoints. All right, decreasing behavior means where am I going downhill, essentially. And so there, as far as going downhill, I'm wanting to look where my graph is, I'm going to say, having a downward approach. So here, looks like we have a downward part. In the middle there, it's constant, and then it looks like from here on down, we have a downhill approach. So there, we're going to do the same thing. Look at the x values. So starting at this point, looks like we're start decreasing. So that we know starts at 0. And then where does it stop? Well, it looks like it stops right here at 2. And then union, since we have another piece. Okay, we're going to look here at where it starts. Looks like it starts here. So that looks like at 4. And then where would it stop? Looks like it stopped also at the 6. So we're decreasing from 0 to 2 and then union 4 to 6. And then the final question is, where am I constant? So constant means that we have no change as we go from left to right as far as an uphill or downhill motion. It looks like we're constant in that area. Looks like we're starting at 2 and ending at 4. So constant from 2 to 4. So the big thing here to remember is that when you're actually writing the answers for these intervals, you never include the endpoints. Whether or not the endpoints are included on the graph or not is irrelevant. All right, so then there's a question of how does increasing, decreasing, and constant behavior relate to the derivative? Remember that the derivative is a rate of change or a slope at a single point. So on here, we're going to notice, and we can even look at the graph that we have above, if the derivative is greater than 0 for each x in an interval, then we know that f is increasing. F prime being greater than 0 means that my slope is going to be positive. Well, if my slope is positive, that's going to indicate I'm going uphill. So we notice up here that if we looked at slope anywhere along this line at a, I'm going to say, instant point in time, then that slope is going to have an uphill slant to it if we're looking at slope of the tangent line. So in there, my derivative was positive, so that would be telling me I'm increasing. Then if I look at decreasing, it says, hey, if my derivative is less than 0, so negative, then that's going to tell me that I'm decreasing. Well, we can see that looking over here. I'm just going to pick a point. There, if we do I'm going to say a tangent line, we can see that we're going to have a negative slope. If we have a negative slope, that's going to force my graph to go downward. And so there I'd be decreasing. And then finally, if we have that my derivative is equal to 0 for every x in an interval, then that's going to tell us that we have constant behavior. Okay? So we look here and we know that the slope of a horizontal line is 0, so anywhere in that interval my slope is 0, then that's going to mean it's constant. All right, there are things that are called critical numbers for a function. And these critical numbers, I'm going to say, are going to be useful for the next couple of sections as far as us determining increasing, decreasing, constant behavior, and then also going forward as far as determining relative maximums and minimums. So critical numbers are kind of a big deal. Okay, critical numbers are defined to be numbers that are in the domain. So that means that we're going to need to pay attention to the domain of a function for which either the derivative at that number is 0 or the derivative of that number does not exist. And so because this is such an important concept, what I'm going to do is I'm going to do a couple of questions where all it's asking me to do is just find the critical numbers. Now, I've made a note here and I've said, hey, it's also important to consider vertical asymptotes, but we don't classify them as critical numbers. So if we have something that's a rational function, it's important that we consider vertical asymptotes, but because of the way critical numbers are defined and the way they're defined as numbers in the domain, then obviously vertical asymptotes are not in the domain because those are values where a function would end up giving you 0 in the denominator. So on this first example, it says find the critical numbers for each of the following, as well as telling where the function might be undefined. So on here, the first thing I'm going to do is make a note of what the domain of my function is. So we notice that this particular function is what we call polynomial. That means that it's just a sum or a difference of positive integer powers of x. We may have things like fractions in the front, which we see the 2/3 here as a coefficient, but it's not a power, so that's not concerning us. So this one is polynomial. And because it's polynomial, then we're going to say that the domain is all real numbers. That means that when I'm looking for critical numbers, I'm not having to worry about possible numbers left out. All right, in this particular example, we will then go and look for a derivative. So in finding a derivative, this will help me determine the critical numbers because the critical numbers are found by either saying where's the derivative 0 or where does the derivative not exist. So step number 1, find the derivative. So on this one, we're going to use the power rule as we go through. So this one, I'm going to keep the 2/3 just as it is. And then using the power rule, the 3 would get multiplied to the front, and then the power would be reduced to a 2. Okay, and then minus power rule on the second part, this would be 2x. And then power rule on the last, second to last piece, that'd be 144. And then derivative of a constant is just 0. By simplifying, this particular derivative will become 2x squared, and then minus 2x, and then minus 144. Now, from this point, if possible, I'd like to try to factor this derivative, and this is something that we're familiar with. So notice that every single one of these factors has a factor of 2 in common, so I'm going to factor that out. That leaves me 2 on the outside, and then an x squared minus an x, and then here minus 72. All right, and then from there, let's see if we can factor the inside piece. So it looks like a nice binomial there. So if it's going to factor, it factors 2. It's a nice trinomial, so if it's going to factor, it'll factors 2 binomials. So we can do an x and an x. And then we need factors of negative 72 that would either add or subtract to the interested negative 1 that we have there in the middle. So that sounds like a 9 and an 8. So here's 9 and here's 8. We want the 9 to be negative and the 8 to be positive so that we get the negative 72 at the end, but the negative 1 in the middle when we add them together. Now that you have this factored, what we're going to do is find the critical numbers in 2 steps. So the first step here to critical numbers is find where the derivative is equal to 0. So f prime of x equals 0. So on here, we have the derivative. So we're going to say 2 times x minus 9, and then x plus 8 equals 0. So on that one, we know that if we have a constant that's in the front that doesn't have a variable with it, we don't have to take that into consideration. So really all we're doing is trying to figure out where x minus 9 would be 0, solving that, and then figuring out here where x plus 8 is 0 and solving that. So on this one, solving this first equation, we're going to get x is equal to 9, and then on the second one, we'll get x is equal to negative 8. So we have now found the values for which the derivative is 0. The second piece of this is determining where the derivative would be undefined. Now, if we have a derivative such as this one that's a polynomial, there's not going to be any values for which a polynomial is undefined. So in this situation, you want to write it down, but then you can kind of scratch it out and say, hey, I don't have any values for which the derivative is undefined in this situation. So coming down here, those values are our only critical numbers. Now, the critical numbers, remember, had to be in the domain. This particular problem, the domain was all real numbers, so we didn't have any kind of problems there as far as maybe needing to get rid of some critical numbers at the end there. All right, let's hop down to a different kind of question. This question obviously is a square root type of function. So this one, what we're going to do is first rewrite it so that here in a little bit it's easier to take a derivative of. So I'm going to write it with a 1/2 power. However, before I get too far, I need to make sure to think about the domain of this function. Well, it's a square root function. So in talking about domain for this function, we can only take, I'm going to say, even roots of positive values. So what we have to do is we have to take the 3x plus 4 and say it must be greater than or equal to 0 for this function to be defined. So now we're going to solve that inequality to determine the domain. We'd subtract over the 4, and then we divide by 3. Be careful, it doesn't happen on this problem, but you know that when you're solving an inequality, if you ever have to divide by a negative, you have to switch the inequality symbol. So in this situation, there's my work for finding my domain. My actual domain is going to be any number that is negative 4/3 or larger. So domain here, we would say negative 4/3 to infinity. So if one of our critical numbers happens to be outside that domain, it's actually not a critical number. All right, from here, let's go and find a derivative. So g prime, we can see here we're going to need to use a chain rule. So we're going to multiply the power to the front. We're going to keep the inside part just as it is. We're going to reduce the power by 1. That would make it negative 1/2. And then we're going to multiply by the derivative of the inside. Inside derivative would be 3. Okay, from here we're going to simplify that. And we're going to say in this particular problem, there's a 3 that's over 1. There's a 2 in the bottom here. I'm going to kind of create a fraction out of that, and then I'm going to say conveniently place the 3x plus 4 in the denominator. It would now be to the positive 1/2 power. So 3x plus 4 to the positive 1/2 in the bottom. And at this point, if you'd like to, you can rewrite it as a root. So from here on out, we're just going to be doing algebra on it. Or if you want to leave it as a power, that's fine as well. I'm actually going to leave it as a power in this situation. All right, now there's 2 situations for finding critical numbers. The first one is finding where the derivative is equal to 0. Now, on this particular problem, our derivative is a fractional type thing. That being the case, the only way a fractional type thing will equal 0 is if the numerator does. So I'm going to make that note. That would mean, in this case, the numerator would equal 0. Well, in this problem, the only thing in the numerator is 3, and obviously it doesn't make sense to say 3 is equal to 0. So this is out. For the second part, we say, where is my derivative undefined? Well, this is a problem where there's a possibility that the derivative could be undefined. Since I have a fractional type function, then the denominator could possibly be 0. Now, in this problem, notice that we have a coefficient of 2 out in the front, and we also have this exponent of 1/2. Neither one of those two things, because they don't involve the variable x, are going to have any influence to the denominator being 0. So on here, the only way that that's going to be undefined is if the denominator equals 0. And the only way that's going to happen is if the inside factor there is 0. So we can ignore the coefficient of 2, we can ignore the power of 1/2. So this will only happen if 3x plus 4 was 0. So in that particular situation, if we solve that, we get 3x equals -4. Divide by 3, so we get x equals -4/3. Okay, now we have to make sure, if that's going to be a critical number, that it's actually in the domain. And we notice that it is in the domain. So is in domain. So that particular value would be a critical number. So on here, we'll say that's a critical number. All right, and that one's it. All right, finally, let's look at a true rational function. So it's a rational function to begin with. And on this one, we're first going to make a note about the domain. So for rational functions, it's going to be all real numbers except for whatever makes the denominator 0. So on this one, we notice the only thing in the denominator is x minus 1. So we'd want to make sure that x minus 1 was not 0. So that would mean if we solve, x could not equal to 1. So we're essentially saying domain would be all real numbers except for 1. And so to write that, we would say domain is equal -infinity all the way up to 1, and then use a parenthesis to leave that out, and then union parenthesis 1 to infinity. All right, from here, to find the critical numbers, I want to take the derivative. So on this one, I'll use the quotient rule. That's not the only way to work the problem, so if you know another way and you still get the same derivative, likely that's going to be okay. All right, for this, we start with the denominator, so it would be x minus 1. And then we take the derivative of the numerator. Well, the numerator is a constant, so that's going to make that derivative 0. And then we do minus, we take the top, the numerator, -2, and then we multiply by the derivative of the bottom. Derivative of the bottom is just 1. And then this is all over the denominator squared. Okay, this is a really simple derivative because the numerator happened to be a constant. So now if we simplify that, the x minus 1 times 0, that's going to go away. That's just going to be 0. And then over here, we're going to have a negative times -2. That's going to be positive times 1. Still going to be positive. So that will be 2 over. And then x minus 1 all squared. All right, now we're in the same situation that we were in last time, in that we're looking at something that's rational. And so the two situations are that we first want to see where the denominator is 0. So where is h prime of x equal to 0? Well, that would be the case only if the numerator were 0. In this situation, we don't have any x values in the numerator, so the only thing we have is 2. 2 is definitely not equal to 0, so this is out. All right, and then the second thing we look at is where the derivative is undefined. So where is h prime undefined? Well, that would occur if the denominator was 0. We said last time that when we work these, if there's any coefficients in the front, we can ignore those. If there's any powers, we can ignore those as far as finding critical numbers. So on this one, The only way that the denominator would equal to 0 is if the x minus 1 were equal to 0. So on this one, we're going to get x equals 1 as a possible critical number. Now on this one, we notice, we go back up here, and we say, oh, that's not in the domain. And because it's not in the domain, then that means it can't possibly be a critical number. Okay? So this one, we're going to say no critical numbers. Now, later on, we're going to have to consider the x equals 1, but we're going to consider it as a vertical asymptote, not as a critical number. All right, from here, let's look at this function and then answer the following questions based on the graph. And you notice here I've labeled so that you're able to tell the coordinates for some special points. It says first, identify the intervals where the f of x is increasing. Well, that's going to mean that my derivative is positive, or I'm going uphill. So on this one, it looks like I'm increasing from, looks like somewhere over to the left up to that point. I would also say I'm increasing in here. So let's give those intervals. Okay, now remember these are open x intervals. So to the left, this graph is going to negative infinity in the x direction. So we'd say negative infinity, and then all the way up to -2, and then union. And then on this one, our x value is 2 where it starts and 4 where it ends. So 2 to 4 on increasing. Okay, identify the intervals where f of x is decreasing. That means I'm going to be going downhill. And so it looks like there I'd be decreasing in here somewhere and also in here somewhere. So let's identify those intervals. Looks like the x values for the first decreasing is from -2 all the way up to 2. And then for the second piece, looks like we're starting at 4 and then ending at 8. All right, then it's asking me, identify the intervals where f prime of x is less than 0. Well, f prime of x being less than 0 means that I am decreasing. So what intervals was I decreasing on? That happens to be the intervals I just wrote down. So it's the same question, just asked in a different way. So on this one, you'll say -2 to 2, and then union 4 to 8. All right, then the next question is, where is f prime of x greater than 0? That's going to mean, where am I increasing? It's just, I'm going to say calculus terms for increasing. So I said that I was increasing originally from negative infinity to -2, and then union 2 to 4. All right, then it says identify the x coordinates where the derivative is equal to 0. Well, we've talked about constant behavior, meaning that derivative is 0. There are also locations where the derivative is 0 at, I'm going to say, a high or low, as long as we have, I'm going to say, smooth curve through those points. So here we can imagine, if we're looking at tangent lines, that these tangent lines are going uphill. These tangent lines are going downhill. At some point in there, there's a tangent line that has a slope of 0, and that happens as long as you have a smooth curve, and I'm going to say there's a point up there. So on this one x value for which the derivative is 0 is x equals -2. All right, there's another such value over here. Right there, the derivative would be 0. We have a nice smooth, I'm going to say, approach to that particular point. So also at x equals 2. Now, from something that we've done earlier, we remember that where you have sharp points, such as this one, the derivative doesn't exist. So you don't want to say that your derivative is 0 there. Okay, the next thing is identify the x coordinates where the derivative doesn't exist. Well, that would be at a sharp point. And so on this one, we can definitely say that's where x is equal to 4. Okay. On these, we don't consider endpoints as far as looking for where derivatives are zero or non-existent. Okay, there's actually a mistake here in the notes. It says identify the location of the values of all relative extrema, maxima and minimum. Those are actually things that we don't do until the next section, so you can just scratch those out. That's always an easy way to get notes done. All right. All right, the next thing I'd like to do is actually test a function without its graph to figure out where it's going to be increasing and decreasing. So the steps here is you first find your critical numbers as well as any values for which the function's undefined. Those would be values like vertical asymptotes. So let me just say, for a simple example, we've been given a function, and let's say we've gotten critical numbers to be x equals -2, x equals 0, and x equals 2. So you're going to plot those critical numbers on a number line. Okay, so you see those critical numbers plotted. Then you're going to choose what's called test values of x around each critical number and plug in to f prime. So in this situation, we could choose possibly x is -3, x is -1, x is 1, and possibly x is 3. And we're substituting these values into the derivative. In the derivative, we're going to find out if the derivative is positive or negative. If we find out in plugging one of our test values in that the derivative is positive, then that is indicating, hey, the function's increasing in that particular region. If we find out that it is less than 0, that's saying that the function's decreasing in that region. If we find out that it's equal to 0, then that's going to tell us the function's constant in that region. So that's the main idea of using critical numbers and a number line and test values to determine increasing, decreasing behaviors. So let's go ahead here and look at kind of a nice example. So this example, it asks, find out where the function's increasing and decreasing. Within that question, they're indicating, hey, you need to find the critical numbers. You need to, I'm going to say, kind of think about the domain of this function as well in doing that. So let's go ahead and write down what the domain is. This particular problem, it's a polynomial type function. So the domain is just all real numbers. So we're not going to have any kind of problems there as far as having to eliminate possible critical numbers. Okay, let's find the derivative. So here, we would keep that 2/3 constant. And then this power on the x to the third, that 3 would come to the front. And then it would become x squared. The next piece over, its derivative would be 2x. Second to the last, its derivative would be -4. And then derivative of the 2 at the end would be 0. Let's go ahead and simplify that. The 3's would cancel out. And then we would have a 2x squared. And then minus a 2x minus a 4. Now, as we did before, we want to go ahead and see if we can factor this if possible. So we notice everything has a 2 in common. I'll factor out a 2. And then that's going to leave me with an x squared and then minus an x minus a 2. I'll go ahead and go on from there to see if we can factor further. So it looks like an x and an x. And then we need factors of -2 that would add or subtract to the interest of -1 in the middle. So I think that would be a -2 and a +1. All right, now for critical numbers, we're saying where's the derivative 0 and where's the derivative undefined. So if we're doing where's the derivative 0 first, then in this particular problem, that would mean that whole thing would be 0. So 2 times x minus 2, x plus 1 would be 0. The 2 coefficient in the front doesn't have an x value with it, so we can ignore that. This would be something that I'd want to set to 0 and solve. And then as would this other piece. So on the first one, the values that would make that 0 would be 2. And on the second piece, the value that would make that 0 would be -1. Okay. Because our domain was all real numbers, then those guys right there are my critical numbers. All right, now what you do is you take those critical numbers and you place them on a number line. So on here, make sure when you're placing them on the number line, you put them in the order they come. So in other words, -1 is first, and then over here somewhere is 2. Only put the critical numbers. So in other words, at this point, because this is polynomial, we don't have any vertical asymptotes, anything like that. So the only critical numbers are -1 and 2. If we did have vertical asymptotes, we would want to place those on there, but not classify them as critical numbers. But you don't want to put any other increments in there. You don't want to put 0, 3, 4, -2, anything like that. Just those values. Then what I'm going to do is above and below those, I'm going to put like a little dotted line. And all this is doing is visually breaking up the number line for me so that I can see what I'm doing. Then what we're going to do is we're going to test values in between, I'm going to say each critical number. Obviously there are values to the left of -1, so I want to test something to the left of -1. So I'm going to test -2. And what I normally do is I circle them so that I can tell that's a test value, not a critical number. Then pick something nice between -1 and 2. The nicest thing I know there is 0. So I'm going to do that. And then pick something to the right of 2. We could use 3. Now, what you want to do with these test values is you want to plug the test values into the first derivative. So we have a really nice expression for our first derivative, and that is here. So we're going to come down and basically say, hey, we're going to evaluate f prime at -2. And the only thing we care about when we get done here is just the sign of our answer. We don't care about the number, we only care if it's positive or negative. So on this one, we'll say it's 2, and then times -2 minus 2, and then times -2 plus 1. All right, so the 2 is obviously going to be positive. And then we're going to multiply that, -2 minus 2, that's going to be a negative number. And then we're going to multiply that, -2 plus 1, that's going to still be negative. So we're essentially multiplying a positive times a negative, which would be a negative, and then times another negative, which would end up being overall positive. So because this is positive, that means that my function is going uphill in that region, which is going to mean that it's increasing. All right, so I put my sign in there that I figure out for the derivative at -2, and then I also draw my arrow. Make sure when you're doing increasing behavior, you start low on the left and go up to the right. Okay, now do the second test value. So f prime at 0. So there we would do 2 times 0 minus 2, and then times 0 plus 1. And once again, we're only concerned about just the signs. So obviously 2 is positive. 0 minus 2 is going to be negative. And then 0 plus 1 is going to be positive. So we're multiplying a positive times a negative, that would be negative, and then a negative times a positive would be negative overall. So the sign of our derivative is negative. That's going to indicate to me that I'm going downhill. I'm decreasing within that interval. All right, and then finally, I'm going to do f prime at the last test value, which is 3. So we'll say 2 times 3 minus 2, and then times 3 plus 1. Okay, determining signs, 2 is positive, multiplied by 3 minus 2, that's positive, multiplied by 3 plus 1, that's positive. So 3 positives multiplied together still definitely be positive. So the sign of my derivative in that interval is positive. That's indicating that I'm going uphill, which is indicating that I'm increasing. So now what you do is you take that picture from what you have here and you look at your critical numbers to determine, I'm going to say, what values you're going to use in the increasing, decreasing intervals. And then you also use the uphill, downhill arrows that you have. So on here, we're going to say that we are increasing starting from -infinity and then going all the way up to, and be careful here, you want to look at that number there. You don't want to look at that test value of -2. You want to look at your original critical number, -1. And then there's another place I increase, so I'm going to do union. And once again, you've got to be careful there. Look at your critical number. Your critical number was 2. So we'll say union 2 to infinity. So there's where my function is increasing. All right, and then finally, we're going to write down where it's decreasing. So decreasing, that would only be between -1 and 2. So we'd say an open interval from -1 to 2, and then that's where the function is decreasing. All right, so this one we've taken from beginning to end, everything from writing down what the domain was to finding the critical numbers, and then finally with the green part I have boxed off the actual interval test where I'm determining the sign of the derivative at my test values. All right, we want to just look at a couple of more examples as far as different kind of functions that can be thrown at you. So this one, it's exactly the same instructions. We want to find out where it's increasing, decreasing, but we have a rational function in this case. Okay, this rational function is not quite as nice as the one we looked at earlier, but hopefully shouldn't be too bad. All right, so for this one, we first want to determine the domain. And what I'm going to do is I'm going to do that up here. Got a little bit of extra room at the top of the page. So we're going to do a domain up here. Okay, this one, we notice that it's rational. Being rational, we know the denominator couldn't equal to 0. If we set x plus 1 not equal to 0, we get that x couldn't be -1. So the domain is going to be -infinity to -1, and then union -1 to infinity, not including that -1. All right, now we're also going to make a note, and this is something that we're having to remember from somewhere back when. Vertical asymptotes occur in a rational function in factors of the denominator that don't cancel out. So we notice that this rational function is completely factored. We have an x plus 2 factor on the top and an x plus 1 factor in the denominator. That x plus 1 factor in the denominator is not going to cancel with anything in the numerator. And so vertical asymptotes occur at the values for which the denominator equals to 0 when you have factors in the denominator that don't cancel. So there's going to be a vertical asymptote at x equals -1. Vertical asymptotes are not critical numbers, but they are things that we're going to have to consider when we do our number line test. All right, so now let's go and find the derivative. So g prime of x. All right, so on this is going to be quotient rule. So we keep the top, and then we take the derivative, we keep the bottom, and we take the derivative of the top, and then minus, we keep the top, and take the derivative of the bottom. And then all of that is over the bottom squared. Okay, now we want to simplify. There's not much simplifying to be done. We have a 1 to be distributed for the first group. That's not going to change anything. We have a negative to be distributed to the second group. So we'll have x plus 1 and then minus x minus 2 and then all over x plus 1 all squared. Okay, simplifying there, we notice we have a couple of x's that are going to end up canceling out. And then we have a 1 minus a 2, so that's going to give us a -1 on the top, and then a x plus 1 all squared in the denominator. So for this one, as far as critical numbers are concerned, the first thing you do is figure out where your derivative is 0. So far with rational functions, we've been unlucky with that particular part. We noticed here that it would be where the numerator was 0. Well, the numerator is -1. -1 is definitely not equal to 0, so we scratch that part out. And then for the second part, we would be saying where is the derivative undefined? So there, g prime would be undefined if the denominator was 0. Well, we've said we can ignore powers and coefficients in the front, so the only way this would be 0 is if x plus 1 were 0. So that would mean x would have to be -1. Well, remember we made a note at the beginning that -1 is a vertical asymptote, so there are actually no critical numbers. Well, if there's no critical numbers, how am I supposed to do a number line test? Well, in this situation, you put both critical numbers and vertical asymptotes on the number line. So in this situation, the only thing we have to do is put the vertical asymptote there. So we're going to do a number line. We're going to put -1 on there. But what I'm going to do is when I do the vertical dash line right there, I'm going to make myself a little note that, hey, this is a vertical asymptote, not a critical number. And that's important too for things that we do a little bit later on. All right, so now if I'm doing test values, I want to pick something to the left of -1. So let's pick, let's say -2. And something to the right of -1, let's pick 0. And then we're going to take those values and plug back into the derivative. So here we have the derivative. So we're going to evaluate g prime at -2. And remember here, all we care about is what the sign of the answer is. So we have a -1 over -2 plus 1 all squared. Well, here, the top's most definitely going to be negative because we have a negative number up there. The bottom, no matter what, is going to be positive because you're squaring it all. So in this situation, you have a negative divided by a positive, which is going to give you a negative overall. So this being negative is going to mean you're decreasing, you're going downhill. All right, now do the same thing with g prime of 0. So I'll have -1 over 0 plus 1, all squared. And then notice we have the same thing happening in this problem. The top is negative no matter what. The bottom is positive no matter what. And so we have a negative overall. So on this side, we still have negative. So we're still decreasing. So what this tells us is we're decreasing over our entire domain. We're not decreasing over all real numbers because there's a number in the domain. I'm sorry, there's a number left out of the domain, that -1, but we are decreasing over our entire domain. So what we'll say here is we will say we are increasing nowhere. And that's fine as far as an answer because we're asked where are we increasing, decreasing. And then we're going to say that we are decreasing over the entire domain. So we would say from -infinity all the way up to that critical number. Remember, we look there. So -1, and then union -1 to infinity. So there's our increasing, decreasing behavior for that function. All right, so for our last example, I'm going to look at this root function. And this is a little bit of a, not unusual necessarily, but something that you want to watch for. Notice here that in thinking about the domain, we know for square roots or any kind of even roots, we always want to make sure we're taking square roots of positive numbers. The makeup of this particular problem is nice in that when we look underneath the root, we have an x squared plus a 1. Well, the square on the x is going to ensure that that piece is positive. And then because we're adding 1, that's going to make it more positive. Or I'm going to say at least increase the value. So it's going to keep it positive, I guess I should say. So we're going to make a note here that this will never be negative, just based on the makeup of the function. And so on this particular root, the domain is actually all real numbers. So in looking for critical numbers, we know we're not going to have any kind of issues as far as that's concerned. Okay, so now let's go and think about taking derivative. So the first thing I'm going to do here is go back to my function. I'm going to rewrite it as x squared plus 1 to the positive 1/2 to make it so that I can take a derivative. So derivative here, y prime would equal, I'm going to have to use a chain rule. 1/2 comes to the front. X squared plus 1 stays. The original power of 1/2 reduces by 1 and it becomes -1/2. And then we want the derivative of the inside, which would be 2x. All right, then we want to simplify that as we can. So there's a 2 there and a 2 there that would cancel out. There's this x that's left at the end. That's understood to be in the numerator. And then we have the x squared plus 1 all to the negative 1/2 that would drop down to the bottom and become positive. So x squared plus 1 to the positive 1/2. And you can either leave it as the 1/2 power or you can change it to a root. I'm just going to leave it for right now. Now, in thinking about critical numbers, we want to know where the derivative is 0. That would be if the numerator were 0. Well, on this particular problem, we notice, hey, we have an actual x value in the numerator. So this would happen if x were 0. That one's already solved, so we don't have a problem there. And then number 2, where is y prime undefined? Well, y prime would be undefined if the denominator was 0. Okay, we know that we can ignore any kind of powers that's on entire groups or coefficients in the front. So this would be the case only if x squared plus 1 were equal to 0. Okay, well, if we try to solve that, we're going to need to subtract that 1 over. So we'll have x squared equals negative 1. And then solving, we'd need to take a square root of both sides. Don't forget the plus and minus on the right-hand side. But then when we do that, we're going to get something that's a non-real result. So we see here that we're taking square root of a negative 1, which is going to be basically plus or minus I. So if we have a non-real result, then we're out as far as looking for critical numbers there. So x equals 0 is our only critical number as long as it's in the domain. We said on this particular problem that the domain was all real numbers. So 0 is the only thing we're needing to consider as far as a critical number. So now we jump to the number line. And we're going to put 0 on the number line. And then from here, I kind of split it up. We don't mark that as a vertical asymptote like we did the last time. It's not a vertical asymptote. We want to pick an easy number to the left, let's say negative 1 for a test value. And then an easy number to the right, let's say positive 1. And then from here, we're going to go through and plug those test values into the derivative. So here is the point at which we have a derivative. So let's say we do y prime specifically at x equals negative 1. Okay, so doing that, we're going to have a negative 1 in the top, and then over. Down here, be careful on grouping. It'll be negative 1 squared plus 1, and then all to the 1/2. All right, here, remember, all we care about are signs. So on the top, it's for sure going to be negative. On the bottom, we have negative 1 all squared. That's going to be positive. And then 1 plus 1, that's going to be 2. That's going to be positive. And then when I take the square root, it's still going to remain positive. So the bottom value is positive. So negative divided by positive, negative. That's going to mean this function is going to decrease in that interval. Okay, and then next we want to look at y prime at x equals 1. So there we'd have positive 1 over 1 squared plus 1 all to the 1/2. The top value definitely positive. The bottom value is also going to be positive using the same logic as we did on the prior part. So this is going to be positive overall. That being positive is going to mean I'm increasing. All right, so the only thing we really have to do here is just to write down our final answer as far as increasing, decreasing. So in this particular problem, I'm increasing from, remember we always look back to our critical number, so that was the 0. So we're increasing from 0 to infinity, and then we are decreasing from negative infinity to 0. All right, y'all let me know if you have any kind of questions.